All right, so in this video, we're going to continue our discussion with parametric curves. And in the last video, you saw it was mostly just manipulating them in a basic introduction. Now we're actually going to apply some calculus to these parametric curves. So we'll go ahead and start with letting x equal f of t and y equals g of t. If we're searching for dy dx, then we're going to ddx y, just like we would have in a traditional format, which would of course be the dy over the dx. But since x is a function of t and y is a function of t, the derivative of y is going to have to be with respect to t. So we're going to get a dy dt, and then separately, because once again these are separate functions working together to create a curve, since it's a separate function, the derivative of x would then be the dx dt. So in order for us to come up with dy dx of this curve, we would just do a dy dt divided by a dx dt. All right, so we're going to take a look at an example where we find the equation of the tangent line to this curve defined parametrically at this point. And as we know from earlier problems, a big part of this is going to be dy dx. So our dy dx, remember that's going to be the derivative of y with respect to t over the derivative of x with respect to t. So the derivative of y with respect to t would be our 2t e to the t squared, and then for the derivative of x with respect to t, that's going to give us the 1 over 2 root t. Now you can clean that up if you want to, but I'm going to go ahead and just evaluate this now at t equals something. Now we have to figure out what the t equals. Well, if you kind of reverse engineer this a little bit and we let our x equal 2, if x equals 2, or let's say our e equals y, when we plug that stuff in there, then we can come up with a way of figuring out what t would need to be. So in doing so, I could have a 2 equals 1 plus root t, which if I subtract 1, I get 1 equal root t, and t equals plus or minus 1. But remember, in this particular case, t has to be positive, so t would have to equal 1. You could have also approached it the other way by letting e equal e to the t squared, in which case 1 would equal t squared, and we get to the same result. But remember, we're needing to plug a t in here to come out with what the numerical value is for the derivative or the slope at that particular point. So when I plug that in, that's going to give me a 4e. So there's my slope. Now, when it comes to putting the rest of the equation together, it's pretty straightforward. We would have our y minus e equals our slope of 4e times x minus 2. And cleaning it up just a bit, y would equal 4ex minus 7e for our final answer. Now, that is how to approach this, obviously, using the methods that we're trying to introduce. But from the last video, you could have also eliminated the parameter here and then found the derivative as usual, evaluated at x equals 2, and gotten the same exact result. In fact, I would encourage you to try that after you pause the video. All right, so the first derivative is generally not too bad, but when we come to talking about higher order derivatives, we need to be a little bit careful how we represent this. So let me go ahead and draw this out. The second order derivative of y with respect to x is going to be the same thing as ddx of dy dx, okay? Which is going to be the same thing as ddx of y prime. All things we've discussed in Calc 1. Now, this is of course also going to be the same thing as dy prime dx, and having to treat things separately because we have two functions now, x and y, both with respect to the parameter t. This is going to be a dy prime over dt divided by a dx dt. And so the notation there can get a little bit messy, so we're going to take a look at an example here. We're going to have x equals cosine 2t and y equals cosine of t. So as we work through to find the second derivative, I'm going to spell things out pretty thoroughly here. The dy dt is going to be our negative sine of t. The dx dt is going to be the negative 2 sine of 2t. Okay, so again, just spelled out, the derivative of y with respect to t would be your negative sine, derivative of x would be that negative 2 sine 2t. So then our dy dx would be the dy dt, negative sine of t, over the dx dt, negative 2 sine 2t. And so from there you could clean this up. Obviously the negatives would go away. I would use an identity there. That's going to be 2 sine t cosine t, in which case the sine t's can go away. And when all said and done there, this leaves us with a positive 1/4 secant of t. So that's our dy dx. Now, if we want the second order, then what we're going to have to look at now is the dy prime over dt over the dx dt. And so I want to be clear on this real quick. This dx dt right here is the same dx dt that you have right here. So that part is literally just going to be copied down and replaced right there. So negative 2 sine 2t. Now in terms of this numerator right here, the dy prime dt, that's going to be the derivative of this guy with respect to t. So that's going to give us our 1/4 secant t tangent t. And so it's very important when you work through these second order derivatives that you do spell it apart nice and neat and clearly, because when it gets down to this actual second order derivative, that dx dt would have already been found from up here, and we literally just plug that in. The numerator is where we have to take that second derivative of the y prime. And so this would clean up, and I would encourage you to clean it up with a little bit of trig, and to negative 1/16 secant cubed of t. So that would be our second order derivative.